Hello and welcome to my YouTube channel Advanced Physics, Unfolding the Mysteries of Nature, and I am Sarasri. In this lecture video series, we will be discussing about some concepts in advanced physics, and in today's video, we'll be discussing about condensed matter physics. So this is lecture number 1, which is introductory to this course. But before diving into the concepts of condensed matter physics, let us understand why do we need to study condensed matter physics and what is it all about. So if we search the definition of condensed matter physics on Google, then the definition we find is something similar to this definition. So condensed matter physics is the field of physics that deals with the macroscopic and microscopic physical properties of matter. In particular, it is concerned with the condensed phase that appear whenever the number of constituents in a system is extremely large and interaction between the constituents are strong. So it means that this condensed matter physics is that branch of physics in which the macroscopic and microscopic physical properties of matter is covered. So what are the macroscopic properties? Like electrical properties, magnetic properties, optical properties, thermal properties, and so on. So these are the major macroscopic physical properties that has to be answered using this condensed matter physics concept. Now, in microscopic properties, the atomic arrangement, lattice structure, spin dynamics, all are covered. So these are the things that we understand using this condensed matter physics concept. Now, this condensed phase arises when a large number of particles are brought in a volume and the force of interaction between these particles is very large. So when we let's suppose that we have a large number of particles scattered here and there, and when we bring all these particles closer and closer and closer, then the force of interaction between them increases, and therefore a condensed phase appear out of these uh, interaction. So this condensed phase, the example of this condensed phase, we see these liquid and solids. These are the example of condensed phase. So these are very common examples. So in solids, what we have learned from our basic school education, that this in solids the constituents particle are very close and the force of interaction between them is very large. Something similar for liquids, but in liquids the spacing between the constituents particle is somewhat greater than this solid, and the force of interaction is weaker compared to solid. So, and the force of interaction is of electromagnetic type. So, this is the basic uh, definition of condensed matter physics, and this definition clearly says what we are going to study or understand in this course. Now, again, a question arises. So, why do we need to study condensed matter physics? So, there are various reasons for this. So, we are surrounded by matters, and these matters are by and large condensed matter in condensed matter phase. either solid or liquids. So the whole surrounding, almost all, is condensed matter, and we need to understand the properties of these matter and material so that we can use them for our benefits. Uh, and it also answers some questions which every now and then puzzles us, or we will find that it is mysterious until we have discovered it. So, like we initially humans were puzzled why metal shines and why something is transparent and some materials are not. Why we feel cold. So these are the example. These are the questions that this subject answers. Secondly, this condensed matter physics is very useful. So today we live in the technologically advanced world, and almost every person has laptop or mobile or any type of electronic gadget. So in these gadgets, what we use memory devices, uh, sensors. So all these memory devices, sensors, and the material out of which these things are made are condensed matter. So we need to do research in these material, or we need to understand these materials so that we can use it. The other point is that the range of condensed matter physics is very large. That means its application varies from nano world to astrophysical world. So since it can be used in space physics, that is like in the some in order to know the understand the planets and some other heavenly bodies, and it also has application in nuclear physics. Some of the concepts are used in nuclear physics, so it has very long range, so it can be used uh, in, in other branches of physics also. So this was the basic introduction. Why do we need to understand and what is all about this condensed matter physics? So, today, since it is introductory, and so initially we will not be considering this microscopic structure property of the material, and we will deal with only microscopic, and then later on we will this cover this microscopic property. But today what we are going to do is that uh, understand the physics of solids without considering microscopic structure. So the story of condensed matter physics starts with the measurement of heat capacity of some uh, materials, or we may say initially it was done for gases, but later on for other materials as well. So, so this earlier heat capacity was considered to be, the C was considered to be 3 kb per atom. Or if we multiply this number by Avogadro number, then we have this is 3R. So the CV at volume, constant volume. So the CV was 3R, and this was called as this is today we also call it this Dulong and Petit's law. Dulong and Petit's law. So it says that the CV is equal to 3R. It has some value, fixed value. If you put the value of R, then we have a numerical value. So, but this law or this value does not hold true for all temperature. Means not all temperature. It is valid at room temperature. So, but at low temperature, the value of CV for almost all material does not follow this law, and it drops rapidly below a certain temperature. Now, if we look at the CV of some material, then what we have is, these are the heat capacities of some of the materials, and we can see that it holds true for room temperature, almost approximately true. So for aluminum it is 2.91, for antimony it is 3.03, and but for diamond it is very low. So for diamond the case is very different. uh, can be derived using two concepts. So one is using concept of equipartition of energy, and then one using the concept of harmonic oscillator. Later, and statistical mechanics. So first, we will derive this Dulong and Petit law using the concept of equipartition of energy theorem. So according to equipartition of energy theorem, the energy associated with each atom, or the translational energy associated with each atom per degrees of freedom is, this is half kVt. Now, so since we have 3 degrees of freedom associated with each particle, so this in 3 dimension, this energy becomes 3 by 2 kVt. So this is the translational energy of the atom. Now, atoms also have vibrational energy, and this vibrational energy is also equal to half kVt. So in 3 dimensions, it is also 3 by 2 kVt. So this E translational and this is E vibrational. So total energy E is E translational plus E vibrational. So now this energy becomes 3 by 2 kVt plus 3 by 2 kVt, and this becomes, so this becomes 3 kVt. So now this is the energy of the atom at a temperature T. Now we know that this heat capacity Cv is given as dE by dt, partial derivative of energy with respect to temperature. So now if we insert or use this value of energy, so this is 3 kVt, then we have, this is 3 kV. Now if you multiply this by Avogadro number or then it is molar heat capacity, and this becomes 3 in kV, which is equal to 3 R. So this CV is 3 R. So now we see that this is nothing other than Dulong and Petit. So this is molar heat capacity So next we will consider the concept of harmonic oscillator, which is also the Einstein model. So using that model also we will derive the heat capacity, that is Dulong and Petit Law. So in this video we have learned the simple derivation of Dulong and Petit Law, and the next we will consider the Einstein model. For matter time, thank you very much.